on a multicast group. And the specific group we're going to be working with is 239.1.1.1. We're going to have router BB1 acting as a multicast server. And the way that we can make our router be a multicast server is we simply send ping traffic to that IP address. We can just ping 239.1.1.1 to create a multicast distribution tree. And when we do that, BB1 is going to flood multicast traffic to R1 and to BB2. BB2 is going to receive it, and it's going to flood it out to R1. At this point, R1 is receiving duplicate multicast packets. Which multicast packet does it actually trust, and which one does it actually use? Well, router R1 in this case is going to perform a reverse path forwarding check, an RPF check. In other words, it looks at the source address of the incoming multicast packet, and it says, if I were to send traffic back to that source based on my IP routing table, which interface would I use? In the case of R1, it's going to be receiving traffic from 3.3.3.3, and it's going to be receiving that traffic over its serial 0/0.1 interface and its serial 0/0.2 interface. And it looks at its IP routing table and it says, if I were to send traffic back to 3.3.3.3, which interface would I use? And it would say that it would use serial 0/0.1. And the reason is we're using OSPF, and I have configured the link speeds between R1 and BB1 and between R1 and BB2 to be identical. So R1 would prefer to get back to 3.3.3.3 by going directly up to BB1 over serial 0/0.1. So it's going to trust the multicast packet arriving over serial 0/0.1, and it will not trust and it will not use the packet coming over serial 0/0.2. Router R1 then takes that packet and it floods it out to router R2, which, great news, is our multicast client. It does want to receive that traffic. However, you'll notice BB2 in our topology does not have any receivers directly attached that want to receive traffic for the group of 239.1.1.1. So what do? Router BB2 is going to send a prune message up to BB1 saying, prune this link off, no longer send me multicast traffic over this link. And by the way, router R1 is also going to send a prune up to BB2 because it no longer wants to receive traffic over its serial 0/0.2 interface. So we send a couple of prune messages, and this is going to prune off a couple of branches in our multicast distribution tree, leaving us with what is called the SPT, the shortest path tree, which in our case is going from BB1 to R1 to R2. That's the most optimal path for this multicast traffic to get from BB1 over to R2. Unfortunately, with dense mode operation, we have not yet reached a steady state operation. In other words, this flooding and pruning behavior, where we flooded traffic throughout the topology and then pruned off the unneeded links, that flooding and pruning behavior happens by default every 3 minutes. And if we have many multicast sources in the network and many multicast routers in the network, this could dramatically impact the performance of the network. And as we said before, we're not big fans of PIM dense mode. What we're going to prefer to use instead is PIM sparse mode. Remember, with PIM sparse mode, we have a router in our topology that's defined as the rendezvous point, or the RP. Think of it as a meeting place for all of our receivers. Traffic can flow from the server to the rendezvous point, and traffic can flow from the rendezvous point out to all of those receivers. In our case, router R2 is our multicast client, so it sends an IGMP join message up to router R1, and router R1 then sends a *G join message up to router BB2. And when I say a *G join message, the star represents the source and the G represents the multicast group. So the message being sent from R1 to BB2 says, I want to join the group, the G of 239.1.1.1, but the star, the asterisk, says, I'm not really concerned with who the source is. I don't even know who the source is. I just want to receive traffic from this group. Meanwhile, the multicast server has been sending a register message down to the rendezvous point, and this is an *G register message, the S representing the source, which is going to be the address of BB1. It's going to be 3.3.3.3, and the G is going to be the group. We're going to be pinging 239.1.1.1. So we have this S, G register message coming from BB1 down to BB2. And initially, the multicast traffic is encapsulated inside of this register message. But when the multicast traffic arrives from the source, it arrives at the RP of BB2. The RP tells the router, the source router of BB1 in our case, to please stop sending those register messages. In fact, it sends an S, G register stop message back up to the source router, back up to BB1. This is going to allow a source tree to be created directly between BB1 and BB2. BB2 can then send out traffic via a shared tree out to all the recipients. And in our case, there's only a single recipient. It's router R2. But do you see how the rendezvous point is working? We're sending traffic directly from the source to the rendezvous point, and then the rendezvous point can send traffic out to one or more receivers. Those one or more receivers are sharing the tree that all come back and point to the rendezvous point. And what this has accomplished for us thus far is we have been able to send multicast traffic from the source router, BB1, to the destination of R2 in our case, and we did not have to do the flooding and pruning that we saw earlier, which could, again, adversely affect the performance of the network. But a downside to this approach is we do not have an optimal path, do we? Our path should go from BB1 directly to R1 and then over to R2. Instead, we're going the long way around. We're going from BB1 to BB2 to R1 to R2. Fortunately, sparse mode supports something called SPT switchover. That stands for the shortest path tree switchover. R1 will know at this point that it is receiving traffic from BB1, and it will initiate the construction of a source tree directly between BB1 and R1. What R1 does, it sends an S, G join up to BB1. It knows how to do that because when traffic finally reached R1 from BB1, R1 was able to see BB1's IP address. It knows that it is receiving traffic from 3.3.3.3, so it says, let's stop using the rendezvous point, let's receive traffic directly from 3.3.3.3. So it sends an S, G join message up to BB1, and that allows us to construct this source tree directly between BB1 and R1. However, at this point, it looks like R1 is receiving 2 copies of each multicast packet, one via the source tree and one via the share tree. So what R1 will do, it will send a bit prune message up to BB2 to say we want to prune off this link. And when we prune off that link, we are now able to receive traffic directly from the source without going through the rendezvous point, and we avoided the flooding and pruning behavior. That's why we're big fans of sparse mode as opposed to dense mode. Let's take a look at the syntax we will use to set this up. First, we will want to go into our routers and globally enable IP multicast routing. We do that in global configuration mode by simply saying IP multicast-routing. Then we will want to go in and enable PIM for our various interfaces that are going to be carrying multicast traffic. And we could say that we want to use sparse mode, or we could say we want to use dense mode. But in this lab, we want to demonstrate both dense and sparse mode. So what we will do is this. We're going to say that we want to use sparse dense mode. This tells the interface, use sparse mode if a rendezvous point is available, but use dense mode if a rendezvous point is not available. So we will start out without a rendezvous point defined. That will make us run in dense mode, and then we will define a rendezvous point, and that will make us run in sparse mode. And we said that router BB1 would act as our multicast source, simply by sending a ping out to our multicast CLISD address, but we need a multicast receiver. We're going to make Fast Ethernet 0/0 on router R2 act as our multicast receiver. We can actually have an interface join a multicast group. We do that with the command IP IGMP join-group followed by the CLISD address. And finally, we will want to use sparse mode as opposed to dense mode in our topology. And to make that happen, we will identify the IP address of our rendezvous point. We do that with the command IP PIM RP-address followed by the IP address of the router acting as the rendezvous point, which in our case is going to be router BB2. We will use one of the interfaces on router BB2 to act as that RP IP address. That's the basic theory of multicast and the syntax. Let's now go out to our topology and set it up. The first thing we want to do is to enable the routers in our topology for IP multicast routing.